I'm going to be talking about SAR interferometry applied to earthquake studies. My name is Eric Fielding. I'm a senior research scientist at the Jet Propulsion Laboratory, which is operated by the California Institute of Technology for NASA in Pasadena, California. So we're going to just jump into the INSAR analysis here and not go through any of the theory. The prior knowledge assumed here is going to be that you know about what synthetic aperture radar is, how to process SAR images, and something about the theory of SAR interferometry. And a little bit, I'm also going to talk about SAR pixel offset tracking, which is a slightly more advanced method that is not always used, but is very useful for earthquakes. So earthquakes are one of the big applications of INSAR. Some of the very first published interferograms were for earthquakes. The 1992 earthquake in Landers, California was a famous early interferogram. Earthquakes are often considered as a simplification to be have a earthquake cycle where there's sort of three phases that are separated where the behavior of the fault is different. There's a long intercismic stress buildup phase that could be dozens or hundreds or even thousands of years in some cases. Then there's a rapid coseismic rupture that causes a huge amount of slip on the fault during a few seconds or up to a few minutes. Then there's what we call postseismic deformation, which is additional deformation that happens after an earthquake and typically is over within a few years, but some of the postseismic effects can last decades. And then there's also some faults that don't follow the earthquake cycle, and they move aseismically or slip without earthquakes. So I'm just going to give some quick examples of what how INSAR measures these different parts of the earthquake cycle. This is an example of interseismic deformation on the southern part of the San Andreas Fault. This is the very southern end of the San Andreas Fault near the Salton Sea in Southern California. This black line here is the border with Mexico. So this is the very southern edge of California. And on the left here is the interferogram. It's actually not an interferogram. It's actually a velocity measured over some amount of time with time series analysis. And it crosses the San Andreas Fault, which is this where this red line is, but it also covers three other faults in this area. San Jacinto Fault has two strands, and down here, the light blue is the Elsinore Fault. So this is a little bit more complicated than the typical situation because the deformation is occurring on actually all four of these faults. But we do a profile across the area here. We can see the profile of this is the line of sight velocity in centimeters per year. And overall, over these four faults, it's a total of about 1.5 centimeters per year projected into the radar line of sight. Most of that is on the San Andreas Fault, this first part, but then there's also some amount it's on these other faults. The red dots are GPS data from the many GPS stations in this area. So we can see that the black dots from the INSAR and the red dots from the GPS match very well in this area. after the time series processing. And this is quite this is an older work, so it was actually using IIRS 1 and IIRS 2 data between 1992 and 1999. Then the large displacement during an earthquake. The one example is the 2018 Gorkha earthquake, magnitude 7.8 in Nepal. I'm going to be talking about this more in detail later. This is the large displacement that happens during just a minute or two of the earthquake. So I'll come back to this example with a lot more detail later. Then there's what we call postseismic deformation. And this is an example from the 2003 magnitude 6.5 earthquake near the city of Bam in Iran. And I processed a set of NDSAT SAR images between January 2004 and June 2007, so about 3.5 years. And over here on the right, I combined those together into a time series to show how the surface displacement varies over time. And I'm going to play this movie here showing the accumulation of displacement with time. And also, as you can see, there's a significant amount of atmospheric variation. So some of the time dates, the atmospheric effects are larger than the signal that we want to see. But by the end of the time series in 2007, the final displacement here is quite well imaged. We can see there's an area to the south of the fault. The fault ruptured right through through the center here. This area to the south went up, and then an area right along the fault actually dropped down in a very narrow band. And we did some modeling on this, and our interpretation is that there was, during the earthquake, there was a zone of dilatation where the fault zone was rupturing through material that hadn't been ruptured before, and it caused that material to expand. But then after the earthquake, that material collapsed and caused this subsidence right along the fault zone. So that's an example of postseismic deformation. And this is an example of aseismic deformation, the central part of the San Andreas Fault between the cities of Parkfield and San Juan Bautista. Does not have large earthquakes as far as we know, but it moves gradually all the time at the rate of almost 30 millimeters a year. So this projected into the radar line of sight, it's around only 20 millimeters a year, but it's quite a substantial amount of slip that accumulates. There are some small earthquakes here up to magnitude 3 and a few 4s, but we believe that this section, because it's constantly slipping, does not have large earthquakes. It separates the part of the San Andreas Fault to the north that ruptured in 1906 from the part to the south of Parkfield that ruptured in 1857. Another aspect of INSAR that's useful for earthquakes, this is also from the 2003 BAM earthquake. When we first started looking at the interferogrounds, we noticed the radar coherence or decorrelation, coherence loss was large over both the city of BAM and this adjacent town of Bhairavat. There was this line of low coherence that went out into the desert to the south of the city. And we actually provided this data to our colleagues in the Geological Survey of Iran, and they were able to go to the field and find that there were surface ruptures right along this line of low coherence. And these circles here mark where they were able to map surface ruptures in the field. It was in an area that they didn't expect any surface ruptures. So this INSAR data, the INSAR coherence data was a key data set for them to find the surface ruptures in the field. And another way to look at this is to try to separate the low coherence that's due to the earthquake from low coherence that's maybe due to vegetation or other effects. It turns out that this town of Bhairavat is mostly agriculture. It's full of fig trees, figs and dates. I think it's mostly dates. So we found that by taking the difference between the coherence or correlation between two scenes before the earthquake and two scenes that include the earthquake, we get this correlation change or correlation difference. And that shows very clearly the distinction between the damage to buildings and in the city of Bam from the low coherence that was due to vegetation in Bhairavat. We've since this time made this into a standard product that we call damage proxy maps with a little bit more advanced version of this correlation differencing. This is the location of the earthquake rupture here in the south. Also a clear change. And there was an additional rupture up here to the north that was smaller. So I also want to talk now. I want to talk about some earthquakes in the Himalayas. There's been two large earthquakes since we had SAR data. The 2005 Kashmir earthquake in the western part of Kashmir area caused a large number of fatalities in both the Pakistan-controlled Kashmir and the Indian-controlled Kashmir. And then there was the 2015 Gorkha earthquake in Nepal, which ruptured an area in central Nepal. But there's been a whole history of previous earthquakes, including a very large earthquake in 1505 that likely ruptured as much as 1,200 kilometers in 1505. But of course, with that a long time ago, we don't know the exact extents. And this is just a perspective view showing the whole Indian subcontinent with the plate boundaries. And we can see that not only are these historical earthquakes along the Himalayas, but also along the other plate boundaries to the west and to the east, including the very recent March 2025 earthquake here on the Sanggang plate boundary in Myanmar. So most of the earthquakes have been on plate boundaries, but there was also a large and devastating earthquake here called the Bhuj earthquake near the city of Ahmedabad that caused a huge number of fatalities. It's not directly on the plate boundary, but it's sort of close to the whole plate boundary system on the western side of the Indian subcontinent. But today I'm going to talk more about the Gorkha earthquake. This is one that we had excellent SAR data for. It was a magnitude 7.8. There were at least 9,000 fatalities in Nepal. I think a few in parts of India nearby. There were no significant surface ruptures mapped. We can see that in both the SAR images and the field geologists went to check. And we can see also this so the star shows where the earthquake started. That's the epicenter of the earthquake. But the earthquake then ruptured to the east and ended about 120 kilometers away, well to the east. And then there was a large aftershock of the 7.8. There was a magnitude 7.3 that I'll also discuss briefly. So the first data that we got from INSAR for this earthquake was an interferogram from the ALOS-2 strip map mode. The JAXA ALOS-2 satellite radar Pulsar 2 has several modes, including a strip map mode where it does, or fine beam mode, where it has a 70-kilometer wide swath. It covered the central area where the earthquake damage was generally located, but it did not actually reach the epicenter to the west or the eastern end. It did cover the area of Nepal, of Kathmandu, the capital of Nepal, of course. And we can see that the area around Kathmandu actually went up, got closer to the satellite. In this case, the satellite is to the west. The line of sight from the ground to the satellite is up and to the west. But these GPS vectors show that the slip vector is very close to the along track direction. So we're basically seeing vertical motion here. And there's downdropped area to the north. Then subsequently, we used this early image to show an area of low coherence or decorrelation in the area around the airport of Kathmandu. The airport is this red line. And we found that there was quite a significant area, probably of liquefaction and ground disruption. And our colleague, Professor Roger Billam from Colorado, went to the field and actually found some ground failures where this liquefaction caused. It's not a primary fault rupture, it's a secondary rupture. Then on May 2nd, the JAXA acquired the first ScanSAR scene. This is the 350-kilometer wide swath mode of ALOS-2. This is actually wider than Sentinel-1 or the plan for NISAR mission. It's ScanSAR, so it actually uses bursts and subswaths to cover the full width. Don't have time to go into the details of how ScanSAR works, but it's a way to acquire large swaths. It has some advantages and disadvantages. And again, so this is from the descending track. The previous strip map scene was from the ascending track. The descending track is even more parallel to the earthquake displacements. So this is surely all pure vertical displacement, because the displacement in the direction of the radar of the along track direction is not going to show up in the regular standard interferogram like this. This is the interferogram from the 7.3 aftershock. Again, they got another ScanSAR image on the 5th, 16th, 14 days later on the 16th of May. And we were able to make another interferogram. And we can see the same type of pattern with uplift to the south and down drop to the north, which indicates a buried thrust fault. And by combining the two, we can see that the 7.3 earthquake basically filled in sort of a gap where the 7.8 didn't fill in this corner over here. So it filled in part of the area that didn't rupture in this earthquake, but there's still large areas, especially to the south of the rupture, where we know there's the active main Himalayan thrust, but there's no sign of any displacement in the INSAR data. So there's a significant risk of future earthquakes, both to the south and to the west. The area to the east was largely ruptured in 1934, so the risk of further to the east is less. Another technique that we use, as I mentioned earlier, is pixel offset tracking. I don't know if any of the SAR course lectures went into pixel offset tracking. It's a way of using the amplitude images instead of the phase, and it's a cross correlation method. And the big advantage for this case is that it can measure the horizontal displacements in the along track direction. So we used data from the Canadian RadarSat-2 satellite that was provided by the MDA company. And the pixel offset tracking measures the displacement in the along track direction, and we can actually see the large horizontal displacements that were due to the earthquake. And there's another special SAR analysis method that we call along track interferometry. This was implemented for ALOS-2 data by a postdoc that was working with me, Shunrun Liang, and he made this along track interferogram from the ALOS-2 ScanSAR data. Basically, it's a type of double difference interferogram where you take one interferogram with the part of the azimuth aperture that's looking forward, and another interferogram with the aperture looking backwards. Subtract the two, and you get the along track displacements as an interferogram. And this particular interferogram is plotted with 50 centimeter contours. So there's up to 2.5 meters of horizontal demotion caused during this earthquake, the main 7.8. So we also did analysis of the ALOS-2 and RadarSat data to make a slip model, a slip inversion. This slip inversion was done before we had the ALOS-2 along track interferograms. So it used only the azimuth offsets from the RadarSat-2 data. But we combined these interferograms and the GPS measurements and teleseismic body waves in a joint inversion to estimate where the slip is. These contour lines are the final slip contours. This is a side view of that slip model showing the slip on each patch of the fault up to 6 meters of slip on these patches. And this is actually a joint inversion between the seismological data and the geodetic data. So it actually includes the amount of slip as a function of time during the earthquake, which I don't have time to show in any detail. But it's all published in this paper, UA et al., 2017. This is more information about how the satellite system works, with the animation of how it covers the whole Earth in 12 days, actually covering it, the land area of the Earth, both ascending and descending every 12 days. The S-band radar has a lower duty cycle, so it will only be acquiring data over selected areas, primarily over the Indian subcontinent, then a few additional areas around the world. But the L-band data will be global. The one big difference between NISAR and the other radar satellites is that it's looking to the south. It's looking to the left of the satellite orbit. So that means that it's going to lose coverage of the very northernmost part of Greenland and some of these other islands in the Arctic, but it's going to gain coverage of almost the entire continent of Antarctica, with only a very small hole near the South Pole. So that's going to be a new capability that is not available from other SAR satellites. There's a lot of other information here. It includes polarimetry. Most of the data is going to be acquired in what we call dual polarization, just an HH and HV polarization. But these some of these purple areas on this map are areas that will be acquired at two polarization, at full quad pole, 4 polarizations. There's also some area in the Himalayas where they're going to be doing that during the winter to better image the cryosphere of the Himalayas. We're going to be using the sweep SAR technique. This little animation over here on the right shows how we use a number of receivers and transmitters on the satellite to bounce off this reflector, and then receive over a long period of time to get the full 240 kilometer swath without using a scanning. It's continuously sweeping across the whole width of the swath. So it ends up with data that's more like a strip map, but with the wide swath. So I'm going to be talking about how to work with the SAR data. We're going to not show how to do SAR interferometry processing, but actually work with some pre-processed SAR data. The Sentinel-1 satellite has a number of products. This is sort of the background. The data products that ESA produces include raw data, single look complex, and ground range detected amplitude products. But the JPL projects called Opera and Aria have been producing higher level products from the Sentinel-1 data. The Aria project produces geocoded unwrapped interferograms, the GUNW, S1 GUNW files that are very similar to what we're going to be getting from NISAR. NISAR also has GUNW files. So it's a good example of what kind of data we're going to be getting from NISAR, so I'm going to be talking about that. The Opera project also produces radiometrically terrain-corrected products for the Earth to do other the dynamic surface water extent mapping. And also they do displacement maps for North America only. And they are releasing the co-registered SLC products in co-registered geocoded SLCs, which are also going to be similar to the NISAR products. So NISAR will be having the L-band products processed by NASA JPL and archived at the NASA ASF archive site. The S-band data products will be processed by ISRO. We have a common data format. The same software should be able to access either data set, and their data is going to be archived at their ISRO portal called Bunidi. The data products include the radar coordinates SLCs, the RSLCs, the radar coordinates wrapped into ferrograms, but only for the areas of ice sheets. They're going to be making radar coordinates unwrapped into ferrograms globally. And then they're going to be producing these level 2 products, which are all geocoded. There's going to be a geocoded SLC product, which is very similar to the Opera co-registered SLC product, geocoded unwrapped into ferrograms, which are, as I mentioned earlier, similar to the ARIA Sentinel-1 GUNW products. And then there's going to be geocoded covariance matrix for the amplitude images with terrain correction and the covariance between the different polarizations. I won't be talking about that anymore, but that's one of the data products that's available. So the NASA archive for SAR data is the Alaska Satellite Facility, ASF. It's operated by NASA by the University of Alaska. They had both the data archive and a large downlink station that was specifically built to support NISAR with a 4 gigabit per second downlink capacity. And then they also have various user services, including supporting some on-demand processing. They have the Sentinel-1 SAR original data from ESA, and then they have these derived products that I mentioned from ARIA and Opera, all at the ASF. They have the full set of ALOS PALSAR, the first ALOS satellite globally. They've started getting the archive of ALOS 2 PALSAR 2 ScanSAR data. JAXA has decided to release the ScanSAR for the globe for no charge through the ASF, and they're in the process of transferring that very large volume. We're going to be using the ARIA S1 GUNW files. Those are searchable from the Alaska Satellite Facility data portal, search.asf.alaska.edu. This polygon here is the polygon for an area of an earthquake, the magnitude 7.1 earthquake that happened in July 2019. So it's now 6 years ago. And we can search for that data and download the GUNW file, which is a NetCDF geocoded unwrapped interferogram that we're going to be using later for the rest of the analysis. This is the way that the interface looks. You have to choose the data set here, S1 ARIA S1 GONW. When you do that search with that polygon that I mentioned earlier, and the date interval between the 1st and the 18th of July 2019, you'll get this set of interferograms that cover the earthquake. The earthquake, this area of many fringes here in the middle. We're going to work with the descending track 71 data product in this demonstration. These are instructions on how to open the data with QGIS. The QGIS is a open source and free software, GIS software that runs on Windows, Mac OS, and Linux. So it's a very widely available and free software. It knows how to read these netcdf files directly. The ARIA GONW files end up with a .nc for netcdf suffix. The NISAR products, GONW and other products, have a .h5 ending, but they're actually the same netcdf format. It's just a netcdf and HDF5 are really two different names for the same thing. So you can find your data set once you've downloaded it from the ASF and add it to load into QGIS. And then it opens the netcdf file. The GONW product has many, many layers to it. We can choose which layers we want to display. And for this demonstration, we're going to look at the amplitude, coherence, unwrapped phase, and connected components, and also the ionosphere estimate. The ionosphere at C-band is much less important than it is at L-band, but the ARIA processing has now included the ionospheric estimate, which uses the same split spectrum method that we're going to use for NISAR. The exact structure for the NISAR GONW files is slightly different, but it has the same kind of multiple layers all in one big file. And this is the coherence layer. We can see, just like we saw with the BAM earthquake in Iran, that there's this area of low coherence along these lines in the desert. Ridgecrest is in the eastern part of California, where it's a desert. And these areas of low coherence, or black areas, are basically all the surface ruptures and associated disruptions due to the magnitude 7.1 earthquake and also a 6.4 or foreshock. And because all these layers are geocoded, we can also combine these data sets with other data sets such as OpenStreetMap, as shown here in the bottom. So now I'm going to get out of the slide mode here and go to QGIS directly. This is the coherence map with the OpenStreetMap. We can also combine the coherence map with the unwrapped phase. This is the coherence map with the unwrapped interferogram. Once we have loaded the layers into QGIS, we can then change the properties. This is for the coherence layer. I set the coherence layer to be blending mode multiply here, so that it then multiplies the amplitude of the coherence with the color from the unwrapped phase. I went into the unwrapped phase and set it to be pseudo color with this red-green color map. We could change the min-max values here if we want. That would be a little bit more stretched version. This would be less stretched, minus. So you can adjust the colors as you like for your particular purpose. One of the reasons that I'm showing, that I started showing this unwrapped phase with the combined with the coherence, is that, in fact, if you look at the details of the unwrapped phase, right along the fault, it's not unwrapped correctly. And that is in the areas where the coherence is very low. But it's the unwrapped layer has values there. It's just that they're not reliable. That's why you want to use this coherence layer to select the areas where the unwrapped phase is reliable. Another way to do that is with this layer that's called the connected components. This is the connected components layer. We set this to this is another layer that you could use to get now the area that's not to as a mask to get the reliably unwrapped part of the interferogram. That requires a little bit of extra work in GDAW or using the raster calculator. But you have to combine these into a virtual data set first. Another layer that I wanted to show is the ionospheric estimate. In this case, the ionosphere at C-band is relatively modest amount of displacement of phase. And so in this case, it only goes from minus 9.4 to 8.5 radians. We can change this to pseudo color. It looks like a dramatic amount of here, but this is all less than one, just about 1 radian of a variation of estimated ionosphere, whereas the unwrapped phase for this earthquake is almost 300 radians from positive to negative. So that's a quick introduction to how to work with these GUNW files. The NISAR GUNW files will be very similar. They're going to have the same ionospheric correction layer for L-band data. The corrections are going to be much more important. They're also going to have an amplitude layer that you're going to need to stretch here. Maybe stretch even more. Sometimes you want to combine your interferogram with the radar amplitude. You can play with the amplitude values to get the stretch that you want. These desert areas tend to have a very wide range of values. The very bright reflections from the mountains with the very rough surfaces, and the almost zero reflections from the valleys where it's very, very smooth. So this is my preferred way of looking at the interferograms. It's a good introduction to how to work with the interferometric data. We don't really have time to go into how to work with the modeling. That's a whole nother topic. It would take another hour. So I think this is a good time to wrap up and go to the questions.